Hi, and welcome to 4.7 Normal Force. Number one, an apple has a mass of about 136 grams and is happily sitting on a table. Draw a free body diagram of the apple below. All right, every free body diagram starts the same way. You just draw a box. There's not a lot of space here, so I'm going to have to write over the letters. Anyway, you draw the box, and then you could draw a dot in the center. And now you draw all the forces that are acting on this object, and they're all coming from the dot. Not going into the dot, but coming out of the dot. That's like, if you follow the same rules, then it makes the diagram easier to analyze instead of having some forces go into the dot, some forces come out. Anyway, so it says it's just sitting on the table. So I always kind of start with the same way. If you're on Earth or in another planet or moon, you're going to have a force due to gravity acting straight down. That's always a good place to start. Now, if that's the only force acting on this apple, if you look at the diagram, we're showing that the apple must be accelerating downward through the table because there's only one force acting on it right now. There's actually another force acting on the apple. It's sitting on a table. So there's a normal force acting on the apple. A normal force acts perpendicular to the surface. Normal means perpendicular. And the apple's on a table, it's on a surface, and it acts like that, up. In this case, the normal force is going to be equal to the weight, because those are the only two forces, and the apple is in equilibrium. The net force is 0 newtons. We know that because it's not accelerating anywhere. It's not going anywhere. It has a constant velocity of 0 meters per second. So since there's no net force, the forces must be balanced. There's only two forces, so Fg has to be equal to the normal force. B. What is the mass of the apple in kilograms? And it says the front of your reference table might help you convert grams to kilograms. So they tell you the mass is 136 grams. You look at the front of your reference table to find the conversion factor. So when you're converting, it's helpful to set up a conversion factor. It's the same process every time. Because how do you know if you have to multiply or divide? Well, you first set up the fraction, then you want to cancel out the grams eventually. So the grams are in the numerator here. Let's put them in the denominator here so that they eventually will cancel out. And we want to go into kilograms. So how many grams are in 1 kilogram, or how many kilograms are in 1 gram? You look at the front of your reference table. It tells you the prefix kilo means 10 to the 3. So that means 1 kilogram is equal to 10 to the 3 grams. If you do this multiplication, you do 136 times 1 divided by 10 to the 3 divided by 1,000. And when you get really good at these, if you know the scientific notation, then you could just move that many decimal places, 1, 2, 3 to the left. That's two different ways to do it. 0.136 kilograms. A small amount of kilograms is equal to a pretty decent amount of grams. Okay, C. What is the normal force acting on the apple? The normal force, well, we know the net force is equal to the sum of all the forces. So now we said before the net force is 0 because it's in equilibrium. We could calculate what Fg is. Let's calculate what Fg is. Fg is equal to mg. Fg is equal to the mass times negative 9.8. So that's equal to about 1.33 newtons. And don't forget your units. You don't want to get points off for units. These are kilograms. This is meters per second squared. Okay. So the weight is negative 1.33 newtons. So you get negative 1.33 for Fg plus Fn. You do that math and you get Fn is equal to positive 1.33 newtons. And it makes sense that you get a positive number because the normal force points upward. Number 2. A pensive elephant, shown to the right, weighs 6,000 pounds. Pensive just means deep in thought. Just like you are. Deep in thought. So it says, what is the weight of elephant in newtons? Alright, so they give you 6,000 pounds. And you want to convert, so it's a good thing to set up a conversion factor. And you want to get out of pounds, so you put it on the opposite side of the fraction. You want to get into newtons. Now you look, 1 pound is equal to 4.45 newtons. So we're going to multiply. So 6,000 pounds is equal to 26,700 newtons. And that's Fg. That's the force due to gravity. It's the weight in newtons. And it's acting downward, technically. All right. So it says, what is the mass of the elephant? Well, if you know Fg, the weight, you could do Fg is equal to mg. 26,700 newtons is equal to the mass, which is what we're looking for, times negative 9.8 meters per second squared. And remember, the weight is negative as well because it's acting downward. So the mass is equal to 26,700 divided by 9.8, or 2,724 kilograms. Okay. Now it says, what is the normal force acting on the elephant? It would help to draw a free body diagram if you're still not sure of these. What are the forces acting on this elephant sitting here? Well, you have Fg, and it's just sitting on the stump. So you have a normal force acting upward. If Fg is equal to 2,700, oh no, that's the mass. If Fg is equal to 26,700 down, then the normal force is equal to 26,700 newtons going up, because in this case they're equal and opposite. They're balancing each other out. The elephant is at rest. So Fn is equal to 26,700 newtons in the positive direction going upward. Okay, number 3 says, this section of the homework involves problems where the normal force won't always be equal to the weight, like we just did on the previous 2 that was equal to each other. These are a little bit tougher. It says, okay, so let's do it. Number 3, a 6 kilogram box is resting on a table. What is the normal force acting on the box? So, you know, this is still pretty straightforward. You have Fg acting straight down and the normal force acting straight up. It's going to be business as usual. Fg is equal to mg. Fg is equal to 6 kilograms times negative 9.8 meters per second squared. So the weight, Fg, is equal to 58.8, or let's round it to 59 newtons. Negative 59. It's going down. So the normal force is 59 newtons going up. All right. So far they're equal to each other. Let's see if it gets tougher. Now, B, you push down on the box with a force of 8 newtons. The box still remains at rest, in equilibrium. What is the magnitude of the normal force acting on the box? Hint, draw a FBD, free body diagram, to help you. Let me zoom in here. Let me try to make this a little bit more clear. You have Fg, and you also have a normal force, but we're not sure, is the normal force equal, or is it greater than or less than the weight? You're pushing down on the box. This is your applied force, and that's equal to 8 newtons. The weight is the same, 59 newtons. Since you have the weight acting down and the applied force acting down, and it's still at rest, the normal force has to balance out both of these. So the normal force must be 59 newtons plus 8 newtons, or 67 newtons upward. If we wanted to calculate this, we could say that the net force is equal to the sum of all the forces. The normal force plus the weight plus this new applied force. Now the net force is 0 because you're still at rest. It's not accelerating, so the net force must be 0. We're looking for the normal force. Let's pretend like we didn't do that mental math over there. The weight is 59 newtons downward, so it's negative. The applied force is 8 newtons downward, so that's negative. So you get 0 is equal to Fn minus 67. You add 67 to both sides, and mathematically we could see that yes, the normal force is equal to 67 newtons, which is greater than the weight, right? The weight was 59 newtons. Normal force in this case is 67. It's greater than the weight because the normal force has to balance out the weight and the applied force. Using that thought process, we could do the rest of these problems. It says, what would be the normal force on the box if you pulled up on the box with a force of 8 newtons? It says, okay, so here's our diagram. You have Fg acting down, and you have applied force with your normal force, and these two forces acting upward have to balance out the force acting downward. So what do you think? Is the normal force going to be equal to the weight, greater than the weight, or less than the weight? Let's find out. The mass and the weight stay the same. It's still 59 newtons downward. We didn't change the mass at all, so and we're not on a different planet, so the weight is always going to stay the same. 59 newtons down. You're applying a force upward of 8 newtons. We're looking for the normal force. Let's set up our equation. Don't be afraid of this equation. It's the sum of all the forces. So you write down all the forces that you just drew on your diagram. Fn plus Fa plus Fg. It doesn't matter what order you put them in. Now, are you accelerating? No, you're still at rest. So your net force is 0. Your normal force is what you're looking for. Your applied force is 8 newtons upward, so you keep that positive. Your weight is 59 newtons downward, so you make that negative 59. See, you'll get a different answer. The negative signs are very important. Forces are vectors, and we show the direction of these vectors mathematically using a negative sign. It's super important that you don't drop a negative or make things negative when they shouldn't be. Anyway, 0 is equal to the normal force, and then you're going to get minus 51 newtons. So Fn is actually equal to 51 newtons in the positive direction. So now in B, it was 67 newtons. Now it's less than the weight, 51 newtons, because, the ground doesn't have to work as hard because the applied force is helping the ground out to balance out this weight. So the normal force in this case is less than the weight. Okay, knowing that, try the other ones here. It's the same process for D. You just got to think about it a little bit. Draw that free body diagram. Let's see, for D, what would the normal force on the box be if you pulled up on the box with a force of 25 newtons at an angle of 40 degrees above the horizontal? You got to draw your free body diagram. The weight is acting straight downward. It's still the same box. The weight was 59 newtons. There's a normal force, Fn. We're not sure what that is. you're pulling up at an angle of 40 degrees above the horizontal. You could draw that like up and to the left, up and to the right. The way I drew this, I'm going to have to draw it that way. Let me give myself some room. Okay. Your applied force is at an angle, 25 newtons. This angle is 40 degrees with the horizontal. Okay. Let me try to make my pen a little bit smaller here. Okay. So, it turned red. So, that didn't really work. Okay. This is the applied force, the X component of the applied force. Some of it is going to the left. Some of it is acting upwards. So we're interested in the component acting upwards because that's the one acting on the same axis as the normal force and the weight. So we need to figure out what FAY is, the Y component of the force. You should be familiar with sine, cosine, and tangent by now. This shouldn't be a big deal for you. FAY is equal to FA. In this case, it's opposite the angle, sine theta. FAY is equal to 25 times the sine of 40 degrees. So the component of the applied force acting in the Y direction, it's 16 newtons. Okay, 16 newtons acting up. So now we're ready to do our net force equation. So the net force is equal to Fn plus Fg plus Fa in the Y direction, Fay. You can't just plug 25 in because some of that is acting in the X direction, and we're not summing the forces in the X direction. We're interested in the Y direction because that's the direction that the normal force is acting. Normal force doesn't act in the X direction in this case. All right. You're still at rest in the Y direction. It doesn't say you're pulling it upward and it's leaving the table. So in the Y direction, you're not accelerating up or down. Okay. You're looking for the normal force. Fg is equal to 59 newtons in the negative direction. And Fay is 16 newtons in the positive direction. So 0 is equal to Fn minus 43 newtons. So the normal force, you add that to both sides, you get 43 newtons. I'm kind of liking the smaller pen. Okay, let's see. 43 newtons there. Number 4. A 600 Newton person is standing in an elevator. When the elevator is moving upward with a constant velocity, what is the net force acting on the person? If the velocity is constant, you're not accelerating. If you're not accelerating, A is equal to the net force over the mass, right? If this is 0, this must also be 0. The net force is 0 newtons. No math really necessary. You just know that because it says constant velocity, meaning it's not accelerating, meaning there's no net force acting on it. Now it says, what is the normal force acting on the person? Well, they tell you the person is 600 newtons. Is that the mass or the weight? That's right, it's the weight, Fg. If Fg is equal to 600 newtons, if we draw our free body diagram, and you're moving at a constant velocity, these two forces must be balanced. If this is 600 newtons, the normal force is 600 newtons. So Fn is equal to 600 newtons. You could write out the net force equation like we did on like number 1 and 2, or you could just do it in your head. B, when the elevator is accelerating upwards at 2 meters per second squared. This is what I wanted to get to. Now you're accelerating. So is the net force still 0? Probably not. The net force is the thing that causes you to accelerate. So if you're accelerating, there is a net force. It says, what is the mass of the person? Well, you know Fg is equal to 600 newtons. The gravitational field strength is negative 9.8 newtons per kilogram, or you could say meters per second squared for acceleration due to gravity, and you're looking for the mass. So Fg is equal to mg. 600 newtons downward is equal to the mass times negative 9.8. So the mass of this person is about 61 kilograms. Now it says, what is the net force acting on the person? Hint, think Newton's second law. Newton's second law says that acceleration is equal to the net force divided by the mass, or the net force is equal to ma. We're looking for the net force, right? So net force is equal to the mass, which we just found, times the acceleration. Is that negative 9.8? Is it? Look, the elevator's accelerating upward at 2 meters per second squared. So you even put a positive here, showing the direction. So the net force is equal to, what is that, 122 newtons. That's the net force that's causing the acceleration. Now it says, what is the normal force acting on the person? You know the net force and the weight. Draw a free body diagram of the situation and figure out what the normal force is using a vector sum. So here is the free body diagram. It's still just two forces, Fg and your normal force. So let's do the vector sum thing. The net force is equal to Fg plus the normal force. Be careful. The net force is no longer 0. We just calculated the net force. It's 122 newtons. Fg is 61, no, that's the mass, is 600 newtons acting downward. And the normal force is what we're looking for. So to solve for the normal force, you add 600 newtons to both sides, and you get 722 newtons. This is 722 newtons. This is 600 newtons. The forces are not balanced. That's okay. We didn't break physics. That just means that there is a net force in the upward direction. And that makes sense because you're accelerating upwards. Okay. Now, C is similar. See if you could do C on your own. Do the same process. Find the net force and then do the free body diagram. Okay, so let's do it. It says, what is the net force acting on the man? You're looking for the net force. You're accelerating downward, and you know the mass is still 61 kilograms. So it's a safe bet to say we're going to have to use Newton's second law again. F equals ma. The net force is equal to 61 kilograms times negative 2. So the net force in this situation, since you're accelerating downward, you have a negative net force causing this downward acceleration of 122 newtons. Again, in the negative direction. Now it says, what is the normal force acting on the man? You know the mass and the weight. Draw a free body diagram of the situation and figure out what the normal force is. So here's your free body diagram. You have the weight of the person and you have their normal force You're standing on the elevator. The floor of the elevator is pushing back up on you. But is it equal to your weight? Let's see. The net force is equal to Fg plus Fn. The net force in this case is 122 newtons downward. Don't drop the negative. Your weight is the same, 600 newtons downward. And your normal force is what we're looking for. Now, it's the same process. You solve for n. You add 600 to both sides. But negative 122 plus 600 is going to give you 478 newtons in the positive direction. So in both these cases, the normal force was acting upward, but with different magnitudes. In this case, it's less than the weight. The weight is beating the normal force. It's larger than the normal force, causing a net force downward. That's what's causing you to accelerate downward. All right, hopefully this makes sense. I'm going to do some more practice problems in 4.7 normal force critical thinking. Have a good day.